we like keep neck and neck with our classes, usually pretty close, and to cover this, it took him about 25 minutes, so that's what I'm hoping here. And then actually once we're done with this, we're going to call it a day so I can get to Burlington for a rehearsal. Our daughter is playing in the orchestra, and they needed a French horn, so I'm trying to be very, very small. Small puzzle, so I play French horn. But, so we are definitely piggybacking on this idea. We're going to stick with 0, first and second. Actually, we're just going to go to first and second. And I'm kind of hoping you remember how well, you don't have to remember because you don't have to derive them. But I want you to know that, for first order reactants, there is this relationship. Okay, so the natural log of the concentration at time t divided by the initial concentration is equal to negative k, and k is the rate law constant times the time of interest. So we kind of have time and concentration, that sort of thing. But to get a straight line for first order, we would plot the natural log of the concentration versus time. And if it was a straight line, its slope would be negative, and k is equal to a negative slope. Okay, and then this one over here. So this sort of problem, it's a classic, so you know what that means. Yeah. So this sort of problem basically uses these integrated time concentration relationships for first and second order, so we're going to kind of focus on these two, to basically at a particular time, for instance, get the concentration of A, particular time, get the concentration of A, okay? Or, given a concentration of A, find out what time that would occur. Okay, that's kind of what we're talking about here, okay? So, yeah, first order. Now, I'm going to put another one up here, okay? If we were to, remember, ln is the natural log, base E. So we could actually change this around, take the natural log, or take E raised to the natural log of quantity A over A naught is equal to A over A naught, or A0. And that's equal to E raised to the negative KT. So my point is we can then go ahead and rearrange that, and this is another form of first order. And we're going to need that one too, so I'll kind of go ahead and put that one under here too. These are both for first order. Initial concentration times E raised to the negative KT. Okay? All right. And of course we have this for second order. For second order, this is the integrated time concentration relationship between the initial concentration and concentration at time t. All right. So let's work a problem. All right. So first order, okay, rate constant. It works well for rearrangements and decomposition, so we only have one reactant. Kind of makes things easier for us. So it's first order, so hopefully you're kind of thinking this. And notice it gives us, let's see, first order, the rate law constant, so that's K. So that's K. And it's nice because we said it should be in inverse time, inverse years, that works. That's all great so far. So now here comes the question. It says if a 0.0060 molar solution, that's what you start out with, okay, it's stored at a particular temperature. That K is for that temperature. Actually, tomorrow you guys are going to be doing different temperatures and see the value of K. It's kind of neat. So what will its concentration be after 3 months? So here we go. What will its concentration be? Okay, I think it's this one. What will its concentration be after 3 months? This is kind of what we were up against, okay? The next one is how long will it take the concentration to reach 0.0010 molar from the 0.0060 molar? So here we know this one, okay, and we're going for T, for time. I can't remember which of these we're going to use, but actually we're going to use the other one, okay. You might be, well, how do I know? Well, if it doesn't work, use the other one, okay. Okay. So again, K is given And in the first case, the time of interest is given, and we're after A. I guess that makes sense to use that one. It should work the other way too, though. So it's just kind of plugging and chugging. Okay, the initial concentration was 0.0060 molar. K is 1.65 reciprocal years. The time of interest is 3.00 months. Now, actually, the first step is to go ahead and resolve the whole months and years thing, because we can't. We're counting on K and T to go ahead and make E raised to a power unitless. Okay, so we have to convert. You could go either way, but I think I'm going to go ahead and take the months and go to years. So 3 months, that's our time of interest, times 1 year for 12 months. The months cancel. Yes, this is the sort of thing you still need to be showing factor label. Okay, so our time of interest, 3 months, is really 0.250 years, 3 significant figures. Now we're ready to go ahead and plug in to that relationship you see at the top. Okay, so the concentration at that time should be equal to the initial concentration, 0.0060 molar, times E raised to the negative KT. So times E raised to the negative 1.65 per year times 0.250 years. So years, of course, cancel, which is great. When you're working these, don't forget that, to keep that negative sign with your exponent up there. So when you plug this into your calculator, you should get, and round it to 2 significant figures, 0.0040 moles per liter. That's the concentration of A at 3 months. How did we know that? Because we knew it was first order. And we applied the integrated time concentration equation. That's a good idea. Marie's tapping it in. Did you get it? Yay! I always like it when the numbers match. So let's work the second part of the question. So the second part, we were given a concentration and asked to find the time. Okay, so we can, see, we're going to use the second one. Okay, so, so here we go. I guess we could go ahead and rearrange this, isolating time. Okay, so isolating time, we take the inverse of the negative rate law constant times the natural log of the ratio of A to A0. And we know all of that stuff. So here it goes. So time is equal to negative inverse of K. So time is equal to 1 over negative 1.65 reciprocal years. Now, you remember how this works is we have basically the inverse of years in the denominator, which makes it years. So when we come up with units, actually, this 1 over years in the bottom is going to make years. Notice that this is going to be unitless, which is wonderful. Okay, so, and don't worry, don't worry about the negative sign, because what's going to happen is this quantity is going to be less than 0. Okay, know that, because if you take the natural log of a number that's less than 1, you're going to get a negative number. Okay, so we have 2 negatives, it's being positive. It's wonderful. Units are years. Rounded to 2 significant figures, you should get, 3 significant figures. I think it should be 2. I don't know. In Chem 2, sometimes it's hard for me to track. Maybe it's 3 because, and we'll talk about this because we use a lot of LOGs, log base 10, for pHs. And I think I said before that if you take the log of a number, you show, for instance, 2 significant figures by showing, I don't know, the digits after the decimal, so I suppose. But the point is, whether it's 1.1 years or 1.09 years. Okay. I'm a little forgiving when we're rounding and there's a log function in there. Any questions? That's it.
So if we had a problem like when you want us to do 2 wouldn't matter.
It wouldn't matter. That's the beauty. But I only do that with logs. If you're, yeah, if there's no logs involved, I'm holding you to the, yeah. Yep. Let's do another one. Not so surprising now. This one is second order. So good, bad, or otherwise, you are going to have a sheet on Thursday's test, a week from tomorrow. You are going to have a sheet with these equations. Will they be in this order? Not necessarily. Will they have the graphs? No. So if you're a visual person, you might want to doodle, add to your equation sheet if you want to. So it's second order. Again, only one reactant, which is great. And like we talked about, if the overall reaction order is 2, then units of K are going to be inverse molar, or moles per liter. So inverse moles per liter are liters per mole per time. Okay, so K is great. All makes sense. So here's the question. So this is going to be our A0, isn't it? Okay, our initial concentration is 0.0200 molar. And our two questions are, we only have one equation this time. The first question is, what is the concentration after 1 hour? So time is going to be 1 hour, okay, and we're going to go for the concentration. The next one is, how long will it take for the concentration? So we're going after time, and we have to decrease to 0.0020 moles per liter. So that will be our A. We can do that. Now, if you're like me, this whole this whole inverse of A minus inverse of A0, I don't like the inverses. So a lot of times I will just kind of play along. I'll leave it as the inverse, and then at the end I'll take 1 over it. I'll kind of flip it at the end. Okay, kind of show you what I mean. So we can rearrange this, solving for keeping it as the inverse. We can rearrange this as 1 over A is equal to KT plus 1 over A0. And in the first problem, again, we know the time, we know K, and we know the initial concentration. So this should be fine. So let's plug in. Oh, notice that, and we did this kind of in a few problems we've worked otherwise. If you want to stick with the variable A, which is great because that's how the equations are, you probably should somehow connect how you work your problem, which is just an A, with what the species of interest is for the specific problem. In this case, butadiene, the C4H6. Okay, it's kind of semantics, but here we go. So like I said, I would leave it as the inverse of A. So the inverse of A is equal to KT. So our K was 144 liters per mole hour. That's our K. Times the time of interest, which is 1.00 hours. Notice as we do this, our hours are going to cancel from our KT term. And I'm going to be left with liters per mole, which feels weird, but it's true. Plus 1 over A0. So our initial concentration was that 0.0200 moles per liter. But again, if you look at units here, in the invert, or here we have inverse moles per liter. So when we go ahead and fix this, it's going to be what? Liters per mole. So the beauty of all this is we're going to have liters per mole plus liters per mole, which is wonderful. You wouldn't have to work it this way, but this is the way I would work it. So when you go ahead and simplify that, multiplying the first two terms and then adding the inverse of the initial molar concentration, okay, you get simply the number 194. Now again, 194 carries the units liters per mole, which is just the opposite, just the inverse of moles per liter. So all we got to do is basically take 1 over 94. 1 over 194, sorry. And I didn't show you my notes how we did this, but to get this number right here, all we did was take 1 over 194 liters per mole. And that gives you units of moles per liter, which is wonderful. And the value of the inverse of 194 is 0.00515, 3 sig figs. Okay, but again, these both we worked, and I can't overemphasize this enough. Well, okay. But what you're doing is, right up front, you are knowing what you're dealing with to know which equation to use. There's a little more of a twist. Well, okay, time concentration problems. Oh, we still need to work the second part, sorry. In this part, we were given the molar concentration of A and asked to find time. So this one's not too bad. So rearranging this, we get time is equal to the inverse of the rate log constant K times the quantity 1 over A minus 1 over A0. So that's not too bad. So if we go ahead and plug in the numbers, we get time is equal to 1 over 144 liters per mole per hour. That's inverse of your K. Times quantity 1 over 0.0020 moles per liter. That was our concentration of interest, minus our initial concentration, which is, there's too many zeros and twos here. Initial concentration is 0.0200. So 1 over 0.0200, again, moles per liter. So here we have the inverse of moles per liter unit-wise, and if it's in the denominator, that makes it units of liters per mole, which is going to cancel with our inverse of liters per mole just great. So we're going to be left with units of hours, and allowing yourself, I think, only 2 significant figures. Good. Allowing yourself only 2 significant figures, you'll have units of hours, and the value will be 3.1. Now this is on my calculator where I would play around with the 1 over x key. So in my calculator, I would take, I might take like well, I don't know, I have to play around with it. But I think you hit the 1 over x key and then do 144 times quantity 1 over x 0.0020 minus 1 over x 0.0200 and quantity. And I think that would do it for you. Marie's doing it. Oh, I have x to the minus first. Oh, do you have x to the minus first? Same thing.
Yeah. Oh, okay, we do.
So you
1.4 times
Oh, that's it? And then equals?
2 minus
Oh, the whole way.
0.02 and quantity equals. Oh, I got a syntax error. That can't be bad. That can't be good. I wonder, I think I have to do, I did it, I told you wrong. Yeah. For mine, I was wrong. I have to do 144 and then hit the inverse key.
Okay, so.
Let's see if that works. I think that's going to be better.
I came out with the right answer. Dude, I just put everything in my calculator, like just like that. I didn't do any simplifying first.
But did you use the x to the minus 1 key or the 1 over x key? That's what I was playing.
Oh, the 1 over x, no.
Yeah,
Yeah.
that's what I was.
Oh, okay.
Yeah.
That's what I was trying to figure out.
The
Yeah.
1 over x.
But I have to hit it after I hit my, yeah.
Yours.
Do I even have that? I don't think I have that.
On some calculators, it does either 1 over x or like a over b or something.
Oh, I bet you do. It looks fancy enough.
I don't know. I just know
You
I
should
have a
have
fraction
something.
button.
Should be maybe above
She
your
has-
division key.
A what key?
You're above your division
Yeah.
key. Doesn't say a over
You
b.
can have a look at it.
Yeah,
Wait,
it's
every
What's yours
calculator
look like,
has-
Marie?
has something.
that one.
Okay, good, mine, yeah. So x minus 1.
Oh, there it is. You can use that.
Oh, yeah, that's where I
Or
was.
there's X to the.
Oh, there it is.
Where is it?
Oh, it's right there.
Oh.
I can't never find, if
Wow,
someone
very
says
good.
find this on the calculator, I can never find it.
Well, now you know where it is. I didn't see it either. Yay. Okay, very good. Well, here's the twist. We need to add something to all this. Okay. So remember the other day we had a problem with half-life, and I said, nah, don't worry about it. Half-life is not that big a deal. Basically, all half-life is basically the time it takes to get half of A0. That's it. The time it takes to get half of A0. For A to become half of what you started out with. Have half left. Half gone, half there. Okay. So it's just a special condition, okay? It's a regular time, but we call it half-life, so it's T sub 1/2. And it occurs officially when what you started out with, you have half of it. That's it, half-life. Okay? So we're actually going to kind of go through a proof, and I'm going to kind of add something to these. What is the half-life for, we're going to start with first order.
Is this a classic?
The derivation's not a classic, but using it is. So you don't have to be able to derive it. So if we're going to derive it, all we got to do is do some substituting. So we're going to take the A, and we're going to make it 1/2 of A0. And that, we're going to take the T, instead of a regular T, we're going to make it T 1/2. Then we're going to kind of simplify. So if we make those substitutions, it looks something like this. You're like, holy kalodi. Well, no, we're getting there. Because what do these things do? They cancel out. Is that not wonderful or what? Okay, so now it's getting much better. Okay, so basically you have the natural log of 1/2 is equal to, not quite something that's going to, it can get even simpler. Natural log of 1/2 is equal to negative k t 1/2. Now I don't know if this is your law of logs. Let me pull mine out. But maybe, no, I don't see it.
The next one isn't. It's just they rearranged it.
Just rearrange
Yeah,
it.
they just divided it.
So, like, the log of 1/2 is equal to the log of, negative log of 2. Maybe it's coming up. So you're right, Olivia's right. We're just rearranging it here. I have one more step. This was what I say, this last step between here and here. The log of 1/2, if you have 1/2, is basically the same as the log of the thing that's in the denominator, but you take it times a -1. So that's all we did.
So you pretty much put this number in the negative log, but then it's a log before negative log out.
Yeah. So for this quantity is equal to the natural log of 2 times -1. And then if you buy that, we kind of flatten that out, and so we have a -1 times a minus k down here, and they annihilate each other. So we get basically the inverse of k, the natural log of 2. And that, finally, is something to write home about. So down here, if it's first order, then your half-life, I'll write it up here because I'm not in the room. Your half-life is equal to 1/k ln of 2. Voila, that's it. So just to kind of give you an idea of what half-lives are like, I think this is so cool. So this is just the decomposition of di-tert-butyl peroxide. Okay, so if you start out, and the units here are pressure. So if you start out with partial pressure of 800 millimeters of mercury, in one half-life you have 400. Okay, in the second half-life, it goes from 400 to 200. Okay, In the third half-life, it goes from 200 to 100, okay? And if I was going to do a fourth half-life, it would go from 100 to 50, okay? But notice the half-life looks like it's, what, 80? 80 minutes is the half-life. T1 half is 80 minutes. So every 80 minutes, you get half of what you had 80 minutes ago. I think that is so cool. Okay. So let's do a similar thing for second order. And let's do our substitutions. Okay. Go ahead and we're going to substitute. If we're getting to half-life, we're going to substitute 1/2 A0 for A. Okay, and we're going to substitute our T1/2 for T, and it looks like this. That's not simplified yet. Notice that actually we're subtracting like terms. We have the inverse of A0. We just simply have basically two inverses of A0 minus one inverse of A0 here. Cleaning it up. Okay. That gives you one inverse of A0 term left. Okay. And going ahead and isolating for your half-life time, we get this. And these equations will also be on your sheet, but you have to know how to use them. And actually, kind of looking at this, it makes sense because we said to test for second order, we said you'd plot the inverse of A. Okay? And we said to test for first order, you'd plot the natural log of A. So I guess if I kind of saw those, I would kind of know which is which. Again, you don't need to have to derive this, but you have to know how to use it. So let's see how we use it. Actually, I think maybe I don't have another example. Is this almost done? Oh. Well, I have the homework kind of sketched out to kind of show you, hopefully. So some hints on working these time concentration problems for known first and second order. First, be sure you know you're using the right equation. Okay, that can make a big difference. When I go to grade them, and I get no joy when people don't get the right answer. When I go to grade them, if you don't use the right one, that's a problem. The other thing is, if you don't know if it's first or second order, but K is given, by golly, use that to your favor. Because we said if it's first order, then your units of K are going to be what? Inverse time. And we said if it's second order, your units of a K are going to be liters per mole time, or 1 over moles per liter time. So use that to your benefit. Now, here's the deal. Here's why these little burgers can come in handy. And actually, you're going to use them for your homework that's going to be due on Friday. If you need K and you aren't given K, most likely you're given the half-life. If you need K and you're given the half-life, you can find K. You can find it here, and here you need to be given the initial molar concentration, but you can definitely do that. Okay, so if you're given T sub 1/2 and the initial molar concentration, you can get to K. And I'm going to show you an example of this in your homework. There are times when, let's see, how do I say this? I'm going to kind of emphasize this ratio of A to A0. Do you see where if I would take A to A0 times 100%, do you see where that's basically percent of A remaining? Does that make sense? A to A0. Okay, that's a trick too. So we'll take a look at the problems that are due and kind of see what hints I've got. These are from last year, but I thought they looked okay. I looked at them. Okay. So the first one, it's first order. So, you know, we have, these are our tools if it's first order. What % of a sample remains unreacted after 900 seconds? What did I just say? Okay. Here, we can actually leave it as the ratio of A to A0. Okay. So let's see what my hints were. Okay. First off, don't forget what we talked about earlier with regard to rate law expressions. I can write the rate now, because I know it's first order. Rate is equal to K times the molar concentration of A raised to the first power. Voila, just for kicks. I also doodled all of this stuff just as far as what I can use. Sometimes I may use it, sometimes I may not. So, this is a classic. Well, my kids hate it when I say this is a classic. I bet you do too. Okay. Oh, in this case, we don't have K, but we have the half-life, and we know it's first order. So this is exactly what I was talking about. You can get to K knowing T sub 1/2. That's my hint. Because you're going to need to do that to go ahead and apply this, because you need K. And then don't forget that what you're trying to get to is %, so it's the relative amount that you have left versus what you started with. I would use that one. And leave it as a ratio. My hint here was to remember the law. I couldn't even read my own writing. The log law, that's not low, the log law, basically, if you're trying to get to this ratio, if we take E raised to the natural log of this quantity, that's equal to this quantity. Actually, that's on your sheet. Okay, so remember that. That will help you. Okay. Then B is, what will the rate of the reaction be when the molar concentration of A is down to 0.50? So we're back to our overall just rate law expression. Okay, rate is equal to rate law constant K, which we know because we got that earlier from half-life, times the molar concentration of A. Okay, so that's how you do that. That kind of goes back to what we did before. This is first order again, so I kind of wrote down everything we know about first order, just because the more you write it down, you won't even need that equation sheet, I believe. So in this case, it says, at what time will we have the concentration of A be down to 0.025 moles per liter? So we have the initial concentration, the concentration of interest, and we're solving for time. And in this case, oh, nope. Now I remember. They told us in, not till you get to A, but at the first part, it told you that after 54 minutes, your concentration went from A0 0.800 to 0.100 moles per liter. So to get to K, actually, we're going to go ahead and plug those concentrations in to get to our K. Those concentrations and the time to get to K. Then we're ready to go ahead. Now, once we have K, we can use the same equation. In this case, the concentration of interest is now 0.025, same initial concentration, and solve for time now that we know K. Yeah, these hints might be more confusing than just doing it by yourself. I don't know. I hope not. Then for B, what is the rate of the reaction at a particular molar concentration, kind of like we did for the previous problem. First order again, so we have all this good stuff relating. In this case, we're given, again, the initial molar concentration and the concentration after a certain time. We can use that to get to K just like we did before. Okay, and then go ahead and start in on our problems. Actually, that was the first question, what's K? B, what's the half-life? So the half-life, we're going to use the half-life for first order, because we know K. For C, at what time will the molar concentration be 0.235 moles per liter? This one, I would use the natural log form. And D, what will the molar concentration be after T is equal to 2.5 hours? I would use the exponential form. Okay, So here we have a bunch of ordered pairs, time, concentration, time, concentration, time, concentration. This is actually where you're going to need to use log or pro. And we're back to, they say it's first order, but you're supposed to show that the first order test passes.
So it just needs to be in a straight line.
Yep, needs to be in a straight line when you take the natural log of the concentration versus time, exactly. And then once you have your plot, the beauty of it is kind of like the homework that you guys did today. The slope will be equal to negative K. Oops. Come back here. I think we were about done. Dang, that's a boatload of problems. Oops. Okay. And then C says, what is the molar concentration of A at 750 seconds? I would go ahead and I use the formula. A is equal to the initial concentration times E raised to the negative KT. And last but not least, oh my gosh, there's two more. Second order. So we get to use that second stuff. Looks like this. They give us K, and they ask for the rate of the reaction. Notice it's 0 for B order, so actually when I wrote the rate law expression, its rate is equal to K times quantity molar concentration of A squared. So B does not enter in. So this one's not too bad after all that other ones. Okay, so basically we can knock out rate because we're given K and the molar concentration of A. We're going to square that. That one's, dare I say, easy. So this one, again, you're going to need log or pro, and you're going to plot the inverse of the molar concentration and versus time and make sure it's a straight line. And then from the slope, you're going to take M is equal to K for a second order test. So for each one of these questions then, I would go ahead and use the formula. It says at what time, T, would you have these different concentrations? So it's kind of like the example we worked. Of course, the initial concentration is given, and I would leave it as the inverse and take the inverse at the end. And that's it, isn't it? Okay. All right, so I'll push these out there before I go home. But the lecture probably will wait until I get home tonight, so to be pushed out there. Actually, probably both of them, so I can try to make. Okay. Very good.